Hello and welcome to Soft Papers channel. My name is Godfrey. In this video, I am going to solve Cambridge as chemist. Topic is atoms, molecules, and stoichiometry. This is June 2019 exam series for AS. Topical revision is the best way to get you prepared for your exam. So I encourage you to read a given topic, and when the content is fresh in your mind, come attempt questions on that topic for several years. You can get this kind of questions from this site, softpapers.co.uk. And if you have not already subscribed to my channel, please click the subscribe button and hit the bell icon below. This way you will be notified every time I upload a new video. If you find these videos useful, share with your friends. They also get to get help from the same. Question number 1. Construct an equation for the second ionization energy of argon. Second ionization energy of argon. The first equation for first ionization energy of argon is this one. This is the equation for first ionization energy of argon. Argon loses one electron, becomes charged with a positive ion, and therefore this equation for the second ionization energy of argon will be this one right here, +2 and an electron. Good. Part B, the graph shows the successive ionization energies for the element argon. Successive. Complete the graph with predictions for the 8th and 9th ionization energies of argon. Use a cross for each data. Of course, to do that, you need to remind yourself about the electron configuration of argon, which is this one. I can write it here for you. 2p6, 3s2, and 3p6. So the graph here shows us the number of electrons on the y-axis, on the x-axis, and the ionization energy on the y-axis. You can see we have there are 6. 1, 2, 3, 4, 5, 6, 7 electrons will be plotted here, and from our electronics configuration here, we can see the 6 electrons will be removed from 3p orbital and 1 electron from s orbital. So the 8th electron will be also removed from the s3s orbital. So it is still on the third orbital. So the electron should be somewhere here, not far away. There. Then the 9th electron will be removed from a 2p orbital. So there will be a big energy jump for that electron to be removed right there. And I will place it somewhere here for that to happen. So that's how you remove, that's how you indicate an energy jump from orbital 3 to orbital 2. You need a lot of energy because orbital 2 is closer to the nucleus. So you need more energy to remove an electron which is attracted more by the nucleus from a 2p than 3p. Good. The energy value required to remove the first electron from an atom of argon is circled in the on the graph. Sketch the shape of the orbital that contains this electron. Is circled right here, and the orbital that electron is being removed, the first electron, is on the p orbital, right? So we are supposed to draw the shape of the p orbital. Sketch the shape of the orbital that contains this electron. So this is p orbital. The first electron is removed from the p orbital, and p orbital looks like this. Let me draw a good one. That's how p orbital roughly looks like. Of course, we have s orbital, p orbital, d orbital, and f orbital. Part D. Part D, chlorine exists as a diatomic atom, a diatomic gas, sorry, molecule. A sample of chlorine gas was made during a chemical reaction. When measured, 404 kilopascals at 25 degrees Celsius, the sample occupied a volume of 20 centimeters cubed. Okay. Calculate the mass in grams of chlorine gas formed. For this calculation, assume that chlorine behaves as an ideal gas under these conditions. All right. So what are we given here? We're given pressure. Pressure we are given as these kilopascals. So you can write it as 0.4. Kilo is 1,000, so 1,000 pascals. We are given volume. Volume is 20 centimeters cubed. You change this one into meters cubed. Of course, you multiply by 10 raised to power minus 6. I hope you know how to change centimeters cubed to meters cubed. Of course, centimeters cubed, this is the same. Centi is 10 raised to power raised to power minus 2. But since it is cubed, you cube it. So this is going to be 10 raised to power minus 6. All right, meters cubed. So that is meters cubed right there. Then temperature, should change it into Kelvin. So 273 plus 25 degrees Celsius. This gives us 298 Kelvin. So we have the data there. Therefore, since it behaves as an ideal gas, then we use this equation of equation for an ideal gas, which is this equation. We want to calculate grams. So for grams, for mass, we need N first, the number of moles. Then we convert the number of moles into mass. Mass is equals to moles times volume. Therefore, this is going to be N is equals to PV over RT. In which case, we've gotten P to be, let me write it down here. So we've gotten P is 40,000 times volume, which is 20 times 10 raised to power 6. All of this divided by R. R is 8.31 times temperature of 298. When you do a good calculation with your calculator, you get 3263 times 10 raised to power minus 3 moles right there. We know that the MR of chlorine gas, MR of chlorine gas is 71. Relative atomic mass of chlorine is 35.5. So times 2 gives you 71. So mass that you are supposed to calculate, or I can just take you through the equation of moles. Moles is equals to mass over Rm. Therefore, mass is equals to a mole times MR. In this case, is this moles, 3.263 times 10 raised to power minus 3 times 71. What we get here is 0.23 grams. We're supposed to find the mass of chlorine in grams. So the answer is right there, 23 grams. Part 2. Calculate the number of chlorine atoms in this sample of chlorine gas. You may find it useful to use your answer to part D1. If you are unable to calculate an answer in D part 1, use 0.36 grams. This is not the correct answer. So we're supposed to calculate the number of atoms, number of chlorine atoms. And of course, we know that one chlorine molecule contains 2 atoms. All right, as two chlorine atoms. We know that. So a chlorine molecule will be equal to 3.263 times 10 raised to power 3 times 2, because one chlorine molecule has got 2 chlorine atoms. All right, this is not clear. Chlorine atoms. Therefore, this number will give us 6.526 times 10 raised to power minus 3 moles. Now, we know that 1 mole has got this number of particles, 6.02 times 10 raised to power 3 particles of 23, not 3 particles. Avogadro's constant 23, and therefore this number here, 6.526 times 10 raised to power minus 3 moles, will be how many particles, right? Because you cross multiply, you'll get 6.526 times 10 raised to power minus 3 times 6.02 times 10 raised to power 23. Of course, divide by 1. This should give you, using your calculator nicely, should give you 3.9286 times 10 raised to power 21 chlorine atoms. So the answer is right there, 3.93 in 3SF, or 2 decimal point, times 10 raised to power 21, the number of chlorine atoms. Right there. Part 3. Chlorine molecules does not behave as an ideal gas under these conditions. Right? Does not behave as an ideal gas under these conditions. Explain why chlorine molecules or chlorine gas behaves even less ideally at a high temperature. Now, at high pressure, the molecules are squashed together, so they are close together. So there are strong, there are van der Waals forces of attraction between the molecules. In ideal gas, there is no attractive force. The attractive force between molecules is negligible, is 0. So at high pressure, the molecules are close together. They are squashed together. Close together. Okay. So there are van der Waals. Van der Waals is the intermolecular forces, forces of attraction. So basically that means the existence of van der Waals forces between the molecules of chlorine means it is deviated from ideal gas between the molecules. So chlorine gas will behave as an ideal gas at a very low temperature, low pressure. When you decrease the pressure, then the molecules are farther apart, and therefore there is no van der Waals forces, and consequently no attractive forces. What about very low temperatures? At low temperatures, the molecules also, the intermolecular forces are also significant, and so the collisions are not elastic. So at low temperatures, the intermolecular forces are significant. You remember, when you cool a gas, it will liquefy, or it will condense and become a liquid, and therefore condensation means the gas has intermolecular forces that make it to be solid, a liquid. So the collisions are not elastic, which is one of the properties of an ideal gas. All right. Well, you can get these papers for you to practice. Remember, practice makes perfect. I encourage you to work out these questions yourself as I guide you in this video. You may get these papers I'm solving. You may get this same paper I'm solving right now from this site here, solvepapers.co.uk. The site I'm talking about is this one here, if I may just help you. This is the site I'm talking about, solvepapers.co.uk. In this site, you'll go to A level. Of course, there's physics, mathematics. All of these are solved. And we are solving 2019 topicals. You come here, 2019 topicals. You click there, you'll come to this. 2019 June. We are dealing with 2019 June structured question of atoms, molecules, and stoichiometry. This is the paper I need you to download. And of course, you can also download the rest, both multiples and structured. You can download the rest, and you get all of the papers when you click here. Click here to get all topicals and solved in zip folder. When you click there, you will come right here in this point, in this page. You can get for both 2019 topicals, 2018, 2017, all the way to 2016. Of course, November and June. This is AS. A2. AS is down here. You come here and get for chemist. Of course, there's physics and mathematics. You can ask your parents to help you in acquiring these papers. They're only 10 pounds. Fair price for a good material. Of course, what you need is June is here, structured. So this is what you need to get. You can get as many as you can possibly wish. Practice. You can pay a small price to be able to get your A-star, and that would be a worthy investment. Also, I also do tuition. If you need my help, I can help you. I also have online tuition classes. Of course, I can visit this site, SP Academy, spacademy.co.uk, and the site I'm talking about is this one here. This is SP Academy, is basically Soft Papers Academy. We are online, ICT, mathematics, physics, biology, and chemistry. And I need you to come here and get this step-by-step guide for student dashboard. Also, you can watch this video to get familiar with our online live classes. Of course, you can take time to go through our site and get familiar with what we do. Of course, you need to register. I need you to come here and register. Of course, you provide some details. We'll send you an email to activate your account. Once you do registration, then you can log in and to your dashboard and find a tutor. Of course, you can always get us online, and we'll be able to help you as you prepare for your exam. Don't leave anything to chance when it comes to preparation of your exams. Let us help you get that outstanding grade that you always dream of. Looking forward to see you in my tuition class. That being said, let's go to question number 2. Question 2 is from paper 2-3, and this was number 1. All right, a sample contains 3 different, of course this is May, June. A sample contains 3 different types of atoms. It has argon, potassium, and calcium. State fully, in terms of the numbers of subatomic particles, what these 3 atoms have in common, right? In terms of subatomic particles, you can see the nucleon number. Of course, the atomic mass for argon is 18. Atomic number of argon is 18. Atomic number of potassium is 19. Atomic number of calcium is 20. So they have different number of protons, and they also have different number of electrons, because protons are equal to electrons. But you can see the mass number is the same, 40-40. Therefore, mass number is usually equal to what we call the atomic mass, or we can call it mass number, is usually equal to nucleon number. Nucleon number is protons plus neutrons, right? So you can see all of them. When you add the protons and neutrons in the nucleus of each one of these, will be the same. So we can say, we are said to state fully in terms of subatomic masses what these have in common. So we can now see that all have equal number of nucleons. Equal number of nucleons. Very good. Part 2. State fully in terms of the number of all subatomic particles how these 3 atoms differ, right? You can see they have different number of protons, and therefore they also have different number of neutrons and different number of electrons. So all they all have different number of protons, neutrons, and electrons. Okay, we can basically state here, this is argon, potassium, and calcium, for you to be able to see. Number of protons for argon is 18. For potassium is 19. For calcium is 20. Electrons is also the same, 18, 19, 20. And neutron here is 40 minus 18, which gives us 22. 40 minus 19 will give us 21, and 40 minus 20 give us 20. So you can see that neutrons are different, electrons are different, and protons are also different. The number is different. Okay. B. A sample of sulfur contains only 2 isotopes. 2 isotopes. Isotopes are atoms of the same element with different atomic mass. So it's sulfur 32 and sulfur 34. the relative atomic mass of this sample is 32.09, right? We are given the isotopes here and the isotopic masses right there. Calculate, we are supposed to calculate the percentage abundance or percentage aberrance of the isotopes present in this sample. Of course, let the samples be, let the isotopes be X, right? Let the isotopes, the mass of the isotopes be X, right? So let's see the percentage abundance, okay, of each one of these. So let isotope S32 be X, okay, let it be X, and therefore isotope S34 will be let's say 100 minus X. So with that, we can now write the equation here: X over 100 times 32, this isotopic mass here, okay, plus for the 34, this divided by 100 times 34, and we are told this is equal to this here, is equals to 32.09. Of course, you can multiply by 100 to remove the denominator, times 100 times 100 times 100. So the equation here will be X times 32 over, sorry, we have removed the 100, plus 100 minus X times 34. This should give us, of course, this times 100 will give us 3209. Okay, so this will be now 32x plus, of course, this is in brackets, plus 3400 minus 34x will be equal to 3209. Okay, so then 34 and this will give us 340 minus 2x is equals to 3209. Of course, you can rearrange this equation: 3400 minus 3209 is equals to 2x. Therefore, x is equals to 2x is equals to 191, and x is equals to 95.5%. So if x is equals to 95.5%, then we had said that this will the isotope 34 will be 100 minus x, and we have found x to be 95.5, so this will be 4.5%. Therefore, the abundance for that isotope 32 is 95.5%, and the other one is 4.5%. Very well. Part C. The electronic configuration of sulfur is this. Electronic configuration of sulfur atom is that. Identify which orbital in a sulfur atom has the lowest energy. Of course, the orbital that has got the lowest energy is the orbital that is the closest to the nucleus, and in this case it will be 1s. So the orbital with the lowest energy is 1s. Identify lowest energy. 3p as the highest energy because it's away from the 3p as the highest energy because it is far away from the nucleus. Highest energy. Okay. Since it is away, it is farther away, it is farther from the nucleus. Alright, sketch the shape of a p orbital. Okay, this is no problem. P orbital looks like that. Okay, looks like an 8. You can remember that. Part 3. During the process of ionization of sulfur atom, during the process of ionization, a sulfur atom loses an electron. You can see that right there. So identify the orbital from which this electron is removed. Explain your answer. Okay, so this is a sulfur atom. Then an electron is removed to get a sulfur ion plus an electron. Of course, you can see the ionization energy is the 1,000 kilojoules per mole, and therefore that is a low energy. So that orbital, the energy, the electron should have been removed from the farthest orbital, which should be 3p. Okay. Explanation here is that it is less attracted to the electron in 3p is less attracted by the nucleus, is less attracted to the nucleus, so it is easier to take it fast. It takes less energy to lose an electron from 3p. Very good. Part D. D1. Complete the diagram to show the arrangement of electrons within the third shell of phosphorus atom. Of course, the configuration of phosphorus is 1s. Of course, you'll get it by the periodic table. 2s, 2p, 3s, and 3p. Just got 3. So basically, phosphorus has got 15 electrons. So that is the electronic configuration of that. So complete the diagram to show arrangement in the third shell of the phosphorus. So it has got 2 electrons in S. So the electrons are arranged upside down to minimize repulsion. Electrons are negatively charged. Therefore, to minimize repulsion, their spin is opposite. And of course, we have 3 electrons in p orbital. So each one of the electron will occupy a shell there. So that will be it. Explain why. Part 2. Explain why the first ionization energy of sulfur is less than that of phosphorus. This is a question that is usually asked many times. You can see the ionization of sulfur. We have not indicated. Yeah, it's here. The ionization of sulfur is there. The configuration of sulfur is here. We can write it here to compare with this one of P. So sulfur electronic configuration is 1s, 2s, 2p, 3s, and 3p. Right? So you can see in sulfur the electron is removed from an orbital that has got 2 electrons in 3p orbital. So the electron that is going to be removed from sulfur already the paired electrons are repelling, therefore need less energy to be removed. So we are to explain why the first ionization energy of sulfur is less than that of phosphorus. In phosphorus, we are removing an electron from one of these p orbitals. Therefore, since it is not paired up, you need more energy to remove it compared to sulfur. If we draw the configuration, the 3p for sulfur, you draw the 3p orbital for sulfur. This is 3p orbital for sulfur. The sulfur will have one of the orbital have a paired electron because there are 4. You can see here there are 4. So one of the electron will be removed here. The electron, for first ionization energy, the electron will be removed from this paired up. And when electrons are paired up, they repel each other. Therefore, you'll need less energy to remove. So in sulfur, I can write this. In sulfur, the electron is removed. For first ionization energy is removed from the 2 electrons in 3p orbital. It's removed from here. And when the electrons are paired up, they repel, and therefore the less energy is required. When electrons are paired up, electrons repel and need less energy to remove one. Very well. So that's it for atoms, molecules, and stoichiometry. Topic exam series in June 2019. I hope this has been of help to you. Get more topical questions from softpaper.co.uk, and of course get from this website, and do as many as you can. And if you need my help, you can always get in touch with me in spacademy.co.uk. You'll find me right there, spacademy.co.uk. Then I can be of help to you. Have a great time as you prepare for your exams. Cheers, and see you in my next video. Bye.